For our next speaker, we have Alessandro Tomasiello, and he will tell us about higher spins and Finsler geometry.
Thank you. Let me thank the organizers for the invitation to this very nice conference. This talk is going to be about higher spins and Finsler geometry. And by higher spins, I mean fields with more than two Lorentz indices, which are completely symmetric in this talk. There's some evidence that they play an interesting role in quantum gravity. Actually, when you start, it doesn't look so promising because there are issues already at the free field level, as discussed many years ago, and there's still an ongoing discussion about it. And moreover, when you start dealing with interacting higher spins, you find that there is issues such as basically one is the Coleman-Bandula theorem, for example, that are most easily evaded by taking an infinite tower of such fields. There are exceptions to this rule, for example, if you go to lower dimensions, but by and large, this is the way to go. All this doesn't look so promising at first, but then when you think about it, well, there are theories that have high spin fields, such as string theory. And later, other theories were simpler in the sense of spectrum, but way more complicated in their description. Other theories were devised, notably by Vasiliev, that describe an interaction of infinitely many high-spin fields. So the reason that this is not as exotic as it might sound, well, string theory isn't exotic, at least not in this audience, but maybe you might think that Vasiliev-like theories are exotic, but in recent, one might have thought, but recent years have shown that actually there's a holographic dual, a pretty convincing holographic dual to these theories. Moreover, the duals are sometimes very simple CFTs, such as just a model of several scalars, perhaps coupled to a Chern-Simons field in 3 dimensions. So this, what I just described as the dual to a 4-dimensional Vasiliev type theory. More intriguingly still, it appears that there are some limits where string theory kind of reduces to Vasiliev theory. So notably, there is an example where you consider, well, ABGM, for example, when you take a case, normally we take both ranks to be very large, but if you take one of them to be 1, there is evidence there is a conjecture that says that then string theory fractionate into very smaller fields that are described by Vasiliev-like theory. Okay, so all this is intriguing, and more generally, let's say, even if you don't want to hear about this example, I would say that there's now plenty of evidence that they play an important role in holography. When you have higher derivative operators, basically, there's evidence that higher spin fields. So the higher derivative is some non-causality, more than non-locality, that can be cured by higher spin fields. So they play an important role. I guess this slide is here just to show you that higher spin fields are not enemies of string theorists, rather they should be thought of as allies. So Finsler geometry, on the other hand, might be even less familiar to this audience. I don't know. So if you listen to he's no longer with us, but to Chern, this will be the description. What happens? This will be the description that he would. So he would liquidate the whole explanation of Finsler geometry in this sentence. This doesn't mean that he didn't like it, because he actually worked a lot on it. Okay, already here in these few lines, we have a simple explanation of what Finsler geometry is. So the infinitesimal length is a general function of the axis of your coordinates and of the infinitesimal displacements. So the usual Riemannian case is of this form, of course. And Riemann, actually, the meaning of this sentence is that Riemann already had introduced, so he had considered this in general, but then at some point he started saying, okay, well, for simplicity, I will restrict to this case. So he went on to say, okay, but so the more general case, I'm sure nothing changes. So he was almost right, as we will see. But there are some changes with respect to the usual case that today we call Riemannian. So, well, given that it's such a natural thing to write, you might ask yourself why we haven't considered it so far, and in particular, why in general relativity we usually use this. So have we been lucky? Well, maybe Riemann had this an important insight when he considered this, but perhaps we might as well consider this more general story. Well, okay, so forgetting for a second about this sentence by Chern, let's see more in detail what the previous page meant. So in the Riemannian case, so in both cases, let's say the distance is an integral of a certain function of the position and velocity. And in the Riemannian case, that function is the square root of a quadratic function in the velocities. In the Finslerian case, you can take any function you want as long as it, well, not any function you want, but it needs to be homogeneous of degree 1 in the velocities. Why? Well, because otherwise this length, the length bit of a curve gamma won't be well defined, because if you parameterize it in two different ways, you will get a different result. But if you do this, if you impose this, then this problem won't be there. As we will see, there are generalizations of the standard ideas that you learn in school about connection, curvature, and so on. And well, with some effort, you can also put a minus sign here and consider the pseudo, the analog of the pseudo-Riemannian case. So you can think of, so if you fix x for a second, the position, this function capital F is a function of the sphere, really, because it's homogeneous. So its dependence on the radial velocity is kind of trivial. What counts is really the angular velocity. So if you think about it that way, it makes sense to, so you want to parameterize such a function, and one way is to think about spherical harmonics. So spherical harmonics, how do you parameterize spherical harmonics? Well, they are really just powers of the embedding coordinates, and then, then you need to make the whole thing homogeneous by dividing by the radial, by powers of the radius. I don't know, the L equals 1 spherical harmonics are x over r, y over r, z over r in 3 dimensions. So following this idea, you arrive to this parameterization of, well, I'll often use f squared rather than f to avoid this square root in the Riemannian case. So this G2 is just a shorthand for this guy. And then you have other more complicated things. So it starts quadratic, but then you would like to put here a quartic term, a sextic term, and so on. So this is what this means. But this wouldn't work because it wouldn't be homogeneous of degree 1. So you cure it by just dividing by G2. So now this is homogeneous of degree 2, and so you can consider it. So it's a more general story with respect to this. Would I have what? Why don't I have? No, I could have them only. Yeah, this just because I didn't want to discuss the fact that if I have an even power, I would have to have square root of G2. But yeah, you can consider them. The answer is that they can be there. Yeah, exactly. So this, I don't want to give an example. This is not complete, but you can make it complete very easily. Okay. I didn't like the writing already here, the square root of G2, because, okay, I might as well say it here. Yeah, that's okay, but for the other odd spins, like phi 3 over square root of G2. You could do that. So this is a parameterization. If you sum all over them, including the odd ones in the way that I just said, I would argue that this is a general parameterization. Yours might be an alternative one. You will see why I like this one later. So this is a bit disingenuous in that I'm not saying that this is the only parameterization you can write. I'm saying that this is a parameterization that you can write. The way I wrote it here is incomplete for pedagogical reasons, let's say. I was hoping no one would notice, but in the later we will see why I chose this particular one. It has some virtues. Yeah, there are many others, and in fact, I mean, we'll discuss this because at some point, given that what I will find is nice, but also has some problems, I started considering all sorts of alternative parameterization. Actually, I hadn't thought of the one by Cameron, but I had thought about yours, and we'll discuss in due course why this one is better. In my opinion, you'll see. So. I'm not an expert in either of these topics, but sorry, perhaps I should have said this. This is the central point. So once you get here, with this parameterization, what you see is that you have introduced all these phi s contain symmetric tensors with many indices. So it might be reminiscent of a higher spin field. So we have a theory of so differential geometry, a theory of distance that I will show you in some respects is very similar to what we know already in Riemann geometry, and so you have the potential perhaps to use it for a physical theory, who knows. But in particular, in its belly, it seems to have, or in whatever parameterization we choose, I'm pretty sure in the end we'll hit a high spin field like that. So, okay, this is the naive idea. Perhaps Finsler geometry has something to do with high spin fields. I'm not an expert in either of these topics, but the experts in those two topics didn't seem to bother checking this, so I did it myself. So the plan is to give first a crash course in high spins. I mean, this is probably well known to many people here. Then maybe less familiar is the Finsler geometry, so I'll also give a very quick introduction there. Then I'll pit these two one against the other. So the Franz-Stahl equation is the one that describes free higher spins, and so in that the Finsler geometry is okay, what I just described, and then we will put them together with a nicely alliterating match between Finsler and Franz-Stahl. We will see what happens. So this will be the positive results of my talk. Towards the end, there will be also some less negative news. So the Franz-Stahl equation is comes about by considering, like I said, high spin fields. And well, for now, let me introduce a formal variable ym. You can think of it as analog to the dx that we introduced. I could also call it dx, actually, that we introduced for high antisymmetric fields, where instead of having products there, we would have an antisymmetric product with a wedge. So here there is no wedge, and this is a symmetric product, but otherwise the notation is really similar. I will often need to take derivatives with respect to y, and this will be my notation. So I will just put phi m. If you see phi mu, it doesn't mean that it's a spin 1 field. It might be a spin s field with one derived once with respect to y. So another piece of notation is that if you if you follow this, if you take two product of two such monomials in the y's, well, it's akin to, it basically corresponds to, sorry, here there would be a whole sequence, typo. There would be a whole sequence of y's, y mu1, y mu s, blah, blah, blah. But the message is that just writing one after another is equivalent to taking a symmetrized product of the two higher spin fields. Another piece of notation is the trace. The trace comes about by taking two derivatives with respect to y and then contracting with the metric. So you can consider these high spin fields around flat space or also around the curved space. So using this trace, of course, you can then introduce a decomposition in reducible representations. In flat space, this would be reducible representations of the Lorentz group, let's say. So all these are traceless objects. And, well, okay. So sometimes this is useful. Finally, so this was algebraic. Another piece of notation it introduces this D. I call it D. It's the same, basically the analog of the exterior differential from exterior algebra. Now, instead of taking nabla and then anti-symmetrizing, you take nabla and symmetrize. And you can similarly introduce the adjoint D dagger, similar notation also as in the anti-symmetric case. So let's now, okay, all that was notation. Let's consider now the equation of motion. So by the way, I want to note that we started late. So we take inspiration from the equation from GR. And there, well, this is what you obtain by just deforming around flat space. So in notation of the previous slide, this is what this reads. So then you have, okay, if you know nothing and you're asked to write an equation of motion for high spins, you might as well say, oh, okay, let me use the same operator. This is called the Finsler operator, and I will postulate generalization to a high spin that looks exactly the same. So actually, this is not the motivation behind this equation of motion. The motivation is rather that this operator has nice properties around flat space. So in flat space, you can consider this thing which looks suspiciously like the gauge transformation for an anti-symmetric field, but now symmetric. And if you compute the transformation of this Finsler operator, you see that there are several cancellations, and you end up with something of this form. And so in particular, you can notice that if you take this lambda to have zero trace, then there is the result delta F is invariant. So you can call this a gauge invariance. So this is the peculiarity of the Finsler operator. People then wrote an action, and there is so this is gauge invariant if you also impose a double trace constraint on the field. Some people don't like the fact that there are these constraints, and this has led to many alternative formulations, such as by Francesco Gnotti, who wanted to introduce further compensator fields, because these fields doesn't feel fundamental to some people. But okay, let's leave it like this. Okay, so this was my crash course in, well, okay, one more thing, sorry. In curved space, there is a formula like this, but it's longer, and then in particular it involves the Riemann tensor. So in general, there is no gauge invariance, but in the presence of maximal symmetry and the sitter or the sitter, then the Riemann tensor can be rewritten, of course, in terms of the metric, and you do have a way to introduce a gauge invariance. And this is what eventually led to the Vasiliev theories that is very well-known work in such spaces. Okay, now Finsler geometry. One first thing is that in the introduction I was introducing function of the velocity, and typically people like to think of this velocity as a coordinate of the fiber of the tangent bundle. So we will assign it a new name because it's not nice to be taking derivatives but to this coordinate x dot. but you could do that if you wanted. Coincidentally, people in the high-spin community also introduced a Y that I have considered, but although not very often, but this Y is also very standard in Finsler. Well, now you introduce a notion of the fundamental tensor that is called G mu. It is called G mu because in the ordinary Riemannian case, it does coincide with the metric. But in general, remember that this may depend on this velocity variable. So it's a funky type of metric. And there is a whole discussion to be had about what you do in the pseudo case, because so far I was describing, most mathematicians look at the generalization of the Riemannian case where the distance, all this is to measure distances, but presumably if we want to build a physical theory, we want the analog of the pseudo Riemannian case. And then you need to talk about this guy. And there is a whole discussion of what type of a square should be allowed, because if you are considering such a strange beast. If you have really crazy a square, you might even have more than one Lycon, say, and I guess we don't want that. This whole discussion will be relevant for us, but this is why I didn't want to introduce square roots in the introduction, basically. But, okay, so Conrad was asking about introducing phi 1, why not? And then people have done so, and there is, this is called, this simple thing here, it's just, would just be, come from the action of a charged particle, if you think about it, with this being a gauge field. 5 minutes to say, huh? I guess you're right. So they considered also other cases like that. And, well, we will consider not these cases, but the most general case. Okay, so let me consider concept of connection. If you look at the extremize this, one way to get the connection, even computationally, is to extremize this and you obtain the usual geodesic equation. But the object that you obtain this way, remember that in general will also depend on y. And more catastrophically, potentially catastrophically, you have the thing that if you study how this variable changes on the diffeomorphism, and the changes of coordinates, you see that the dx and the dy transform as vectors in the full tangent. And so basically because of this, you have a non-trivial transformation of even of the simple x derivative. And so this doesn't look like it's going to lead to covariant objects. Luckily, there is an object that does transform without this second term. And this kind of object is the basic building block of all this geometry. It's called the nonlinear connection. So in our usual case, this delta actually reduces to nabla. So in light of this, the most natural connection, which was introduced by Chern, I mean, this is the one that most people use nowadays, is just the same formula as before, but with this delta instead of the usual derivative with respect to the axis. So this is one analog of the Levi-Civita. There is no analog of the Levi-Civita that really has all the properties that you expect in the usual case, but this comes the closest. And then there is a similar story for curvature. There are several objects that you could, there are more objects that you could consider relative to the usual case, because now you can consider derivatives with respect to y as well. But the guy that is most useful for us is just the analog of the Riemann tensor, with the only caveat that here you need to consider this delta rather than the usual derivative. And this combination is typically easier to compute. It has two indices, but remember it's just the Riemann. On the other hand, if you take this, the trace over this, this is more like in its belly it has the usual Ricci tensor if you restrict to the usual case. Otherwise, it's a generalization. I will call it Finsler-Ricci. And now we come to the core, after all this review, to the core of the results. So I decided first to consider what happens under perturbations. under perturbations, you get a formula like, so this akin to what we did for the spin 2 case. We started from, say, from flat space, and we saw what Ricci becomes under a small perturbation. This is what you do if you study gravitational waves, for example. Well, I did the same, and I got a formula that starts like this. Then it's more complicated. It's in the paper. It contains those tensors in the previous slide. But if the original object here is Riemannian, this formula simplifies a lot, and because these objects go to 0, they contain derivatives of the metric with respect to y, which is not there, and then this, the delta and this object here, then they become nabla, and you obtain this formula. This analog Finsler-Ricci at the linearized level, linearized in the phis, the spin fields, is nothing but the Frontal operator of the delta phi deformation, 0. Oh. Well, that's actually better, because this way I get to skip the bad news. But the one thing that maybe the last thing I want to say is that if we now go to the spin expansion, over which many questions were asked, you insert it into the nice formula. The formula still remains nice, but a little less nice. You have the Frontal in the individual spin operators, but those derivatives, this derivative here now acts on the factors of G2 that I had introduced, and so you get another term here. So since I'm out of time, I will just tell you that this creates an issue. What is the issue? The next part would have been called, there's a nonlinear structure, but the next, so this is the hope, and I guess I can keep this as some kind of conclusion. The hope is that you can use this as in the following way. This object that mathematicians introduced would represent the coupling of the particle to the high spin fields. It's naturally like that. And then the high spin equations of motion would just come out as Ricci equals 0, just like in the ordinary case. Because after all, at the free level, they do give the expected operator. And I had to skip it, but there are also interactions that show up if you go beyond the linear level, which I did. And well, this is the hope, but the bad news is that, which luckily I didn't have time to cover, is that there are issues with the gauge transformations, and if you are interested, please ask me about it. Thank you.